Hello, good morning, and thank you very much for watching. This is Mr. Hill dealing with covalent bonds. This definitely is the continuation of the bonds in terms of pure substances, compounds, and mixtures. If there's any questions about the assignments, work, etc., please do contact me. As I've stated at the end of each slide video presentation, which is through Schoology or jhill at lakelandlakers.net. Why do atoms bond? Well, they want to be like the noble gases. They want to fit into the octet rule, which again is when an atom or ion either gains or loses electrons in order to have only eight in its valence shell, if you will. For ionic bonds, they transfer. Usually it's the metal transferring to the non-metal. Like in the table salt, sodium ion is given up, well, sodium atom is giving up an electron to the chlorine atom. And once it takes that, it becomes referred to as a ion and also as chloride, if you will. And it wants to fit into, again, the octet rule. Same thing for the covalent bonds. They want to share two electrons, one from each atom that is a part of that compound if it's only two elements, and it wants to share as like a handshake, if you will, where the hands are the bond and the two people are the atoms itself, or the electrons, I should say, are the electrons, and the hands is the bond itself. All right, so here's a picture of both covalent ionic bonds, and these are pretty decent images here that gets the point across. So you can see for A, the covalent bond has it where both uh, atoms of the hydrogen atom, if you will, are fused together as one. That's a great way of showing it because it can show or give an idea that electrons are forming, if you will, by sharing. There's a pair. Bonds are in pairs. So bonds either is a pair of one, two, and three typically. And with that being said, we have over here the ionic bonding. There's a transfer of the electron to the chlorine atom. Now it's a chloride ion, and that makes up the salt formation right there, or salt compound, if you will. Well, what are covalent bonds? They're chemical bonds that result from the sharing of the outer electrons or the valence shell of the atoms or ions above. Excuse me. It occurs when elements close to each other in the periodic table, as in their electron configuration. Because electron configuration, again, helps explains how bonds between elements are going to behave. And each group on the periodic table is going to act very similar in a chemical reaction. Examples, water, H2O. Also, between non-metals and non-metals happens quite often. And molecules, again, are when two or more atoms bond together covalently. Now, this is for covalent bonds or covalent molecules. Example of molecules is this, and this is a diatomic one, which is fluorine. Then we have H2O, water. We also have ammonia, and then we have methane here. Along with, if you notice, that each of these are nonmetals. And we're going to talk about diatomic molecules right now, actually. So some atoms do not exist as a single atom. Some exist as a pair, where two atoms of the same element exist together throughout the universe. So atoms act and exist as two. And these are the ones, which are, excuse me, hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, fluorine. So we put them together as such. And there are ways to remember them, and we have one way next I'm going to show. And these are referred to as the Magnificent Seven. They refer to as the Magnificent Seven because Either it can form a 7 on the periodic table where they are all located, or in itself, it appears that there are 7 elements. Sometimes there's an eighth one, but for the most part, these are the 7 that are always referred to each and every time. Now, here's a good way to remember that it's very family friendly, I'll say. I have no bright or clever friends. Now, of course, this is not a license to insult your friends to say that they are not bright, but it is a good way to remember, to recall what you're dealing with, if you will. So, there you have it. 3 types of bonds, which are single, double, and triple covalent bonds. Now, in the bonding, if you will, is going to affect the structure in terms of the strength and the durability of those bonds, just to give you a heads up in some type of way. Now, single bonds have it where, of course, straight lines are drawn between each of the elements, and each element in itself appears as represented by its denotation on the periodic table, as in the symbols, and then the lines represents the bonds. Now, the single bonds that we see between 2 carbon atoms in this compound right here, there's only one between them. And then also you have, for the double bonds, there's 2 between 2 carbon atoms. And then for the triple bonds, you have 3. Now, if you're a fan of Wendy's hamburgers and how Wendy's make their old-fashioned hamburgers with the double, single, and triple patties, if you will, or the single, double, triple combo meals on the menu, and I think those are the first 3, if I'm not mistaken. They have square patties. It looks like, if you look at these bonds here, if you look at it, it looks like the side view of a hamburger stacked up, and you can put them together as hamburger patties. As such, you can think of it like that. Now, keep in mind, each bond is a pair of 2 electrons working together. So there's 1 electron from each of the carbon atoms that's being put together here for this bond, and the same with the rest of them. And therefore, if you have 3 pairs for a triple bond, you have 6 electrons being used. So let's look at H2 right here as an example. Now, a single covalent bond has it where each atom shares a pair of electrons, of course, and it's usually 2 between the 2, and it's the longest bond, and it's the weakest of the 3 bonds. Now, if we go over here, in double, you have atoms sharing 2 pairs of electrons, so it's 4 total, right? And it's a medium length. I'm going to talk about this in a moment. We get to the last one. First one was a long, or the longest of the 3 bonds, and then the medium length, as in the double bond. So that means that maybe the limits are going to be different even for the triple bond, and medium strength as well. So it's not as weak as the single. And that's O2 being formed there, by the way. It has a double bond between the 2 atoms. Now let's look at this triple bond. There's basically 6 electrons being used. There's 3 pairs between each atom. And then it's the shortest. So therefore, the more that the bonds increase in bonding, maybe multiple bonds, the shorter the distance begins to be, and also the strength increases. And keep in mind of like the concepts of the periodic table or the periodic trends, where we have things such as the ionization energy, where the closer the valence electron shell is to the nucleus, the more energy requires to pull it away. So there's an attraction, or another way of saying it, there's an affinity for the closeness of electrons and bonds from the nucleus, and from how the electrons in itself are far away from one another in bonding. There's this there's this need to make bonds where things are tighter. The tighter it is, stronger it is. Ionic bonds are like that, which is why nothing that's a salt or ionic bonded material is able to collect electricity until it's actually separated or broken down in water, or what's called dissociated or dissociation. And that's only because the bonds are so tight as a solid for ionic compounds that the electrons cannot flow. They can't move. So carbon, nitrogen, oxygen, and even sulfur are very common to have double and triple covalent bonds. and that example of N3. And carbon, nitrogen, oxygen are things very common in the human body as part of what's called organic chemistry. Bond polarity, very easy to explain this. Looks a little confusing here, but polar bonds and non-polar bonds we're going to talk about. Now, this is a polar bond, and what that means is that there is an unequal electronegativity values for each of the elements involved in the bond. So, for example, if you have a polar bond like hydrochloric acid, for example, HCl, hydrogen only has one electron on its outer shell. Chlorine, I believe, have seven. So chlorine is going to be theoretically 7 times stronger than hydrogen because of the fact that hydrogen only has one, chlorine has seven. So by chlorine having seven, it's going to have a electronegativity much higher, and it's going to pull very aggressively. And usually acids do act very aggressively when they interact with bases or even other materials. Even a weak acid can work over time and actually eat through a substance. Nonpolar is where both elements are equal in their electronegativity, and as a result, they share equally, nice and friendly. There's no aggression between them. And so hydrogen atoms form that as well. And actually, nitrogen as well does that, along with chlorine and any of the diatomic, to be honest with you. For the most part, do the same thing. Multiple covalent bonds. Double and triple covalent bonds are considered multiple bonds, and triple bonds occur when three pairs of electrons are shared. And if you look at it down here, it says wrong that this has too many electrons, and that does right over here. Wrong, no octet. This is correct right here. Yeah, because each one has a pair. So there's two, so there's basically two, four, six electrons there. Each of them get three because each one is sharing an electron, which means it's only the three that they're sharing makes it where each of them only have two left that's not being bonded, which would be why it's represented as five right there. But make a long story short, triple bonds obey the octet rule because of the fact that I can say, oh, I have eight over here because these six plus my two and the same over here. So you have to share them, which make them where they're bonded in that fashion. Covalent properties make it where solids tend to be soft, liquids and gases at room temperatures as well. Low melting points and boiling points. Now keep in mind, low and high are relative to other elements on the periodic table because metals have high melting points where things can be melted at a smoldering degrees of maybe upper levels of 700, 800 degrees. And then you have some things like water that has a very high heat index. It's very interesting. Water is a very interesting compound and act very funny at times. But you have a boiling point, or in this case, a melting point, like for sugar, which is covalent bonded. That's about 340 degrees of Fahrenheit when it starts to actually melt. And if you make that um, sugar melt and add butter at a certain temperature, you can create what's called caramel. And then it's not an electrolyte. They do not conduct electricity very well. So sugar was not going to help you conduct electricity or carry electricity, unfortunately. Now, the strength of the bonds are going to depend on several factors. It's going to depend on the number of electrons. The more electrons shared, the greater the bond. Size of the atom. And typically, we notice that the atomic radius actually increases as you go down the periodic table and over towards the, I believe, the left, if you will. We start getting the metals and things like that. And with that being said, uh, we don't want things creating where, as far as bonding, if you will, to get weaker if you're trying to make a bond be strong. And you also want to keep in mind that the smaller elements are going to be harder to pull away because of ionization energy, and that's going to affect the bonding. Bond length, the greater the bond, the weaker, greater the bond length, weaker the bond is. So the further away it is, so proximity is a big important factor with the strength of bonds. The more they're closer and tighter packed, even smaller, the stronger it is. Also, there is work to be done virtually. You can do the Covalent Bond assessment. It's on like 5 questions. You get 10 tries. Also, go ahead and if you need to contact me, you can email me or use Schoology. Thank you for watching.